I am Dr. Uday Kumar Khan. Good morning to all of you. Today I am going to discuss about the study of dependence of dielectric constant for laboratory experiment. I am going to give you the demonstration of the experiment. Now first we have to understand what is dielectric constant. Dielectric constant is the ratio, dielectric constant epsilon is the ratio of the capacitance C and capacitance C naught when one capacitor is filled with the dielectric material and C0 is the capacitance when the capacitor is filled with vacuum. So C is the capacitance when the capacitor is filled with the dielectric material we want to study, and C0 is the capacitance when it is filled with vacuum. It has it is filled with the, so epsilon is the ratio of C by C naught. Now the frequency of the alternating voltage applied to the capacitor and the epsilon varies like this. If frequency is plotted in the x-axis and epsilon or dielectric constant is plotted on the y-axis, then with the increase of the frequency, epsilon goes down or epsilon reduces. So this is the variation we have to study with from the experiment. Now we have to find out how to calculate the frequency dependence of dielectric constant. So the sample we are going to, dielectric sample we are going to use is the barium titanate. Ba sample dielectric we are going to use is the barium titanate. It has the symbol BaTiO3 and this must be a small letter, and in short it is written like Bt. So we have to calculate the capacitor when capacitor is filled with Bt, and once again when it is filled with vacuum. Now C0 is related with the thickness of the sample and with the thickness of the sample and with the separation of the capacitor plates and with the area of the capacitor plate, like this, epsilon A upon T, where epsilon is the dielectric constant, A is the area of the sample and T is the separation between the plates. Okay. Now we have to we must know now what is the circuit diagram of the experiment. So the circuit diagram for our experiment is like this. We have a sharing bridge. It has 4 arms. Arm 1 contains capacitor C1 and resistor R1. And arm 2 we have the capacitor C2 having value 1000 picofarad. And arm 3 we have the resistance of 3 kilo ohm. And in 4 we have in parallel one resistance and one capacitor which are variable in our experimental setup. And we have this end grounded. CRO is connected here through this LC circuit, and this end is also grounded, and the entire bridge is supported by one AC voltage source having frequency 1 kHz to 50 kHz. So for our experiment, we can vary the frequency of the AC voltage from 1 kHz to 50 kHz. Thus, so this is a AC voltage source, and the bridge is called CRO bridge. And the working formula for our experiment is the following. We can find out the C1, the capacitance value when the dielectric is present within the capacitor. So we have to get the value of the capacitance C1 when the bridge is balanced in the CRO. So balance means the voltage we will get in the CRO, it will give the minimum value when the balance condition is achieved. That is when C4 and R4 are adjusted such that the signal obtained in the CRO becomes minimum. In that case, the value of C1 is equal to C2 R4 by C3. C2 is equal to 1000 picofarad. R4 we can get from our apparatus, and the value of C4 also we can get from the apparatus. We will come to that point. Before that, we first must know how is the sample. So this is our sample, barium titanium, BT. So it has thickness of 2.15 millimeter and the diameter 10.62 millimeter. So from diameter we can get the area pi d square by 4. From this formula we can get the area of the sample. So if we know the area of the sample, we know the thickness, then we can get the value of C0. That means the value of the capacitor C1 when vacuum is present. And with the, if we insert this sample of the dielectric within the C1, then from the balance condition in the CRO, we can get the value of C1. So, taking the ratio of C1 by C0, we can get the value of epsilon at certain frequency of something like, say, 1 kHz. And we will repeat this experiment for the frequency f, changing it in steps of something like 2 to 3 kHz up to we can go 50 kHz. And then we have to plot it here. The frequency, we have to get the epsilon. So we will first have to make a table of frequency and epsilon, and then we have to get this curve by plotting epsilon along the y-axis and frequency along the x-axis. Now we will go to the experimental setup. First we have to understand how to mount the sample within the capacitor sheet. So we will now go to the instrument. Okay, now this is our experimental setup. So the sample I showed you earlier is mounted here. So this is the sample, barium titanate, and so these two spring loaded parts, actually these two are holding the sample tight. So we are making the capacitance between these two terminals. So the capacitor, and this is the one side of the sample, and other side of the sample is connected through this connector. And for better connection, we use aluminium foil under this connecting this insulating material. So we have the aluminium foil here under this white color insulated part, and then we have a metal connector, and we insert the sample here. So between these two pillars, which are spring loaded, we have mounted the sample very tightly. Then these are the coils coming out from the capacitor, and we insert the sample here. Then this is one unit which has inbuilt circuit I showed you for the experiment, and this C1 capacitor is connected here to the circuit with this cable, and we connect the cable this way. This is the cable we connect, and then we take out this signal for the CRO and put it in channel 1 for display. And this part, this unit is again powered by a 5 volt DC power supply, and the AC is generated here within this unit, and the frequency can be varied with this knob, this port, and the frequency can be displayed in this digital display. And the C4 and the R4 of the fourth arm of the circuit I showed you, this C4 can be varied with this port, and this is in the scale of picofarad, and the resistance R4 can be varied with this port. So it has coarse and fine adjustment. So coarse adjustment can be from 0, 1, 2, 3 up to 3 kilo ohm, and fine port can be adjusted with this, and this has a range from 0 to 1 k, and there is a small display. Okay, now we perform the experiment. So we have to set the frequency here, and we have to see the signal here in channel 1, and we have to get the balance, that means the minimum value of the signal. So I switch on here, and this one is also switched on. So this is sine wave. I am setting the value to something like, so first so I set the frequency 1 kilohertz, and this is sine wave. So you can see the sine wave is coming here. Okay. Now the C1, we have to get the minimum value of this. So if I change this, okay, now here also we have to adjust this, we have to select something like here. So I have taken the value something like 1 kilohertz, 1 kilo ohm, and then I am adjusting here something like this, and here I keep the value something like 1500, 1200 or so. And now see, if I change the value of R4, how the signal changes. See, it is becoming larger in amplitude. And now if I reduce it, then it becomes small. It's noisy for some reason. Okay. And now if I so I have taken the value 1500, and now again I am adjusting. So it is again becoming larger. So it's coming down, coming down, coming down. It is coming down, coming down, coming down. It is coming down. It's coming down. Here it is small, smallest. So here the display is a little bit noisy, but otherwise, if you get a clean signal, you can clearly see the picture in this display. When it becomes minimum, when it in the balance condition only it becomes minimum, and in the balance condition we have the value of C4 like something like 1500 picofarad, and R4 we have something like 1900 ohm or 1.9 kilohertz, kilo ohm. So we know C4, we know R4, we know C2, we know C2. Then from the formula we can get the value of C1 when the dielectric present within the capacitor. And now we can repeat the same experiment with different frequencies. Like we can select the frequency something like 3 kilohertz, and then again you have to adjust the value of, and it is becoming less, again it is becoming more, less now, and now we can adjust here. It's becoming more, going down, going down, going down, going down. It's again increasing. So this is the minimum position. So for 3 kilohertz frequency, we have the C4 value 1200 picofarad, and R4 value 1.6 kilo. Again we can get value of C1 for the frequency 3 kilohertz. So you can continue this experiment for the AC voltage frequency up to 50 kilohertz, and then we can calculate the value of C1 for each value of the frequency, and we can make a plot along x-axis frequency and along y-axis epsilon is equal to C1 by C0, and we can get the nature of the curve. We can verify, and it should be like this, as I showed you in the board. So in the manual we have given calculations for a set of frequencies of the AC source, and the value of C1 and C0 also, and we have a given set of data we have taken in the laboratory. From here we can get the variation of frequency and the value of the corresponding dielectric constant, and it clearly shows that with the increase of the frequency, the dielectric constant goes down. So the nature of the value of the dielectric constant obtained in the experiment is according to the theory of the experiment discussed in the beginning of the this video. So I hope you all will be able to perform the experiment in your laboratory, and you'll be able to make your students happy. Okay, thank you all.